Hello and welcome to Meeting C++ Live, the fourth episode today with Tony van Eerd, and we're going to talk about C++ 17.
Hello.
So, Tony.
Hey. Nice to be here.
Yeah. And what we're going to talk about is Tony's C++ 17 examples on GitHub, which you can find on GitHub. I think I linked it even. So if you want to go over that with us together, and maybe if you have questions, go to the chat. That would be great. And so let's get started with the examples. And the file we're going to use is the all-in-one, the first file, which brings us directly to the start. A lot of people have contributed to that. Also, Tony is mostly on his work. So, Tony, as you're part of the committee, and there's a committee meeting this month, maybe let's start with just talking about committee meetings and how C++ 17 got together.
Yeah, and C++ 17 is technically not quite yet done. I think this next week is the meeting in Toronto, where I think is where we finally do whatever last technical dot the I's, cross the T's. It's out for vote. It just has to come back, and I mean it's done except for the paperwork. So hopefully we'll have a big party actually next week, because the committee is already on to everything we talk about now is new features. It's all C++ 20 or whatever number that will be. But yeah, C++ 17 has been the last 3 years of work. Some of it has been even longer, stuff that's been percolating for a long time. There was a lot of, people had a lot of big hopes for big giant features in 17, but the way we work now is what we call the train model, right? Like whatever's ready at this date is what gets shipped. So, you get on the next train. It's not that big of a deal. And of the things, some of the things, like people are hoping for modules, hoping for concepts, hoping for whole piles of these big giant features. If it's not in 17, it's probably in a TS, which means ranges is the other one. You can go find it. So, I think it's working fairly well, this new model.
Yeah, that's exactly it. Modules is available in Visual Studio and the compiler which they use, and concepts is now also available in the newest GCC release, or in last year's GCC release, even like in 6.0. So if you want to play around with that, that's definitely possible. But today we want to focus on what is not in C++ 17. We want to focus on what is, and so let's start this overview with what the hell is if-init.
Yeah, if-init is kind of a funny feature, because it was this was actually a very late feature that showed up just before we were finishing 17. But everyone looked at it and was like, okay, you look at this old code where you could do an assignment inside an if, which works well if your assignment converts to bool, like the if foo star pointer get foo. Yeah, that used to work. But sometimes you get cases where, like this example, which has Q variant here, it's not a Boolean conversion. You need to check is valid. And if you really want to keep your variables local, which you probably should, then you're going to end up with extra curly brackets floating around just to keep this var only accessible when it's valid. So now in C++ 17, you can create the variable inside the if, and then put a semicolon, and then check if it's valid, or do any kind of Boolean check you want, all in one. So it's kind of like half of the, we use the semicolon because it's similar to a for loop, where you have the init clause of the for loop, and then you have the condition of the for loop. So the if now has an init clause and a condition clause. It just doesn't have an increment clause, obviously, because it only happens once. And that showed up, and we're all like, huh, that looks nice. Yeah, let's go for that. And then in the committee, someone was like, does it work for switch statements too? And then everyone was like, well, why not? Should work for if statements or switch statements. So we made it work for switch statements as well. And it's a little feature, but it's kind of one of these little features that makes your code just a little more clear. And and it's kind of nice that you will just see this. People jump to it right away. It's an obvious feature, and you start to recognize new code.
Where can I use this? I see that I can use this in switches and in ifs. Is it also available like in loops? Like is it usable in while or do while?
No. I mean, so obviously it's in the for loop because it was already there. It's not in the while loop. I'm not sure why, but I think if you're at that point, you are one step away from a for loop. Just use a for loop without the increment.
It's specific about if, and then also somehow switch got in it. Okay.
Yeah, it's branching, not looping.
So, and another feature which is very nice combinable with this is structured bindings.
Yep. And structured bindings are another one of these. Just they look really nice, and if you see the syntax, like in my example here, if you look at this C++17 column, it's pretty obvious what's going on. You've got a function that returns, whether it's a tuple or a pair or even a struct, it returns two things, and you can break out those two things out of the tuple with this syntax with the square brackets. And then you get these two variables, I and S, that represent the variables inside that tuple.
So C++ code gets a lot shorter with C++17. I mean, those are now two features that could make our life a little bit easier as a C++ programmer.
Yeah. If we jump down a little bit to the I think it's in here.
You mean to the C++17 compiler output?
The very last example in that structured binding case. Okay. It says arrays, standard array, etc. Oh my.
Okay.
There's an example there using a map with key and value. Mm-hmm. So that's where you really see, this stuff looks really nice. That's valuable to me.
Yeah.
But anyhow, going back up a little bit. It looks like a really simple feature.
Yeah. In
that first example, it turns out because C++ has to be complicated or something. But really it's because of C++ has a lifetime model that's important. So when although it looks simple, you see this function that just returns I and S. It's like, well, did the tuple go away and you've copied the I and S, or where are these variables? And the way it really works is that the tuple still exists, and I and S just point into the tuple. Kind of like a reference, but they're actually more magical compiler references. And I think for the most part, you don't need to know this, but there'll always be that case where it's important to know that variable lived. That tuple is still alive. So
that tuple is not a temporary then?
It's alive for the scope of the curly brackets that you're in. It stays alive. It stays alive as long as it's basically like those variables are like references that extend the lifetime of the thing that was returned.
Okay. So is this different from the tire example then? Is this generating different?
It's only slightly different than the. In that case, it's almost exactly the same. You won't get in the tie example there. You're getting a copy happening because there would be a copy in there somewhere, which you don't get. It would be better if the I and S with the tie were actually references.
Yeah, actually, we can see you show the actual generated code below.
Yeah, so it's more
what the
like
compiler makes from the C++17 code. And there's also a different example of what happens then with the compiler, which actually code is generated. Let's have a look at that too. So instead of you're calling a constructor here, or yeah, a constructor from a struct which has then two variables. So those structured bindings also work on user-defined types.
Yeah. So there's two parts to this, is that if you just have a plain struct, a pod, plain old data struct, they automatically work. It's kind of like a little tiny bit of reflection. It's like the compiler knows that your struct has X, Y, Z, then you can pull those out as if they were a tuple of X, Y, Z. Yes?
There's a question from the chat. Could one have, so is auto the only way to use this, or could one also define like the variable types within the variable names in the brackets?
Right. No, currently the only thing you can do is auto, and you'll notice that, do I have examples? You can do auto ref, or auto const. I think, yeah, I do have examples there.
Okay, so let's go below.
Kind of in the middle. I have an example with an auto, the next one in a B++, auto const, C++, auto ref. All that stuff has to be outside the brackets, and that is actually defining all the constant references is on the variable return from the function, and then the square brackets is how you pull that out. So this function that returns an X is captured as either by the auto on the outside, or the auto ref decides whether that is captured as a value or as a reference. And then the inner thing inside the square brackets is always a reference to that. And my examples hopefully show kind of that. So there's only one weird case in all this, which is the last big example, where I try to really hit home that you're referencing a variable that's is it in this example? Sorry.
I'm not sure. Do you mean arrays in SV array, the last example?
No, not the there's an example in here that has I should have looked at this a little better. Hello structured bindings. Right. The one that says output hello structured bindings, which is actually
I have seen that.
It's the second or third block.
Here.
Yeah.
Let me bring that
in.
So yeah.
You'll notice in this example that struct foo outputs it has a string inside. It outputs its string in its destructor. So this is showing the lifetime of that foo. On the left it has the auto square bracket is equals foo, and then we output hello, and then we change s to be structured bindings. We don't output that s, we just set s to structured bindings. The code outputs hello structured bindings instead of hello world, because foo, which used to hold world in its destructor at destruction time, now holds structured bindings. So the compiler side of the code shows you that there's a temporary foo that was constructed. We outputted hello, and then the code on the left that says s equals structured binding actually does temp stir equals structured bindings. So you're changing that foo that is hidden. There's that hidden variable temp that you can't see anywhere. That is what s is changing. So that thing gets destroyed at the end of the function, and that's what you see output.
Oh boy, you're gonna have fun debugging that.
Yeah, I mean, I think it's another one of these cases where 99% of the time you don't have to think about it. You're just gonna be passing back stuff, and it's just gonna work like normal. And it's just these odd cases that, and they're kind of the odd case where you're like, why did we do it that way? But then if you think even further, you'll be like, oh, I see why you did it that way, because because of construction and destruction lifetimes, it has to work this way. You would get worse problems if we destroyed foo. Obviously we can't destroy foo and keep references to it, and we didn't want to make copies of everything, because C++, you don't want to pay for what you don't need to pay for.
Yeah.
So
we have a special relation to copies.
Yeah. Hope
So
that
let's move on
explains.
to the next feature,
Yep.
which is more compile time, constant expression if, which kind of, it's not exactly what static if would be, but it's kind of a static if, or a better enable if for C++ 17.
Yeah, yeah. And my giant example here is mostly the same. And what I'm actually showing in this example is it's kind of combining the previous feature. Here's a class foo where I want to write my own interface to structured bindings. I want my foo class. It's not a plain struct.
Okay.
I've got private members, but I want them to work with structured binding. So I happen to, for whatever reason, this class, I wouldn't really write a class that has private members, but then give you references, functions to reference those private members.
Okay.
I would just make it all public. But if you had something like this, in C++, without using Constexpr if, then you would have to. The whole idea of how to interface with structured binding is you have to implement tuple size for your type and tuple element, so that's what structured binding uses to figure out your class.
Okay.
And tuple element, which is return the right, and then also get. You have to implement get.
I see, and then so in 14 you need to specialize tuple element t for each member of the tuple, and in 17 you're able to kind of override std get, or the get for this. Well, it's not in the namespace std, so it's not std get, but you kind of write your own get method for foo.
Yes.
And then you're able to see.
If you look at the
this constant expression
side,
if which element you want to return.
Yeah, on the left-hand side, you have to specialize get 0 and get 1. You have to define get as a template and then specialize get 0 and get 1, which isn't that bad, but it really confuses people as to it's not the natural way of doing something like that. Now in 17 on the right side, you just have one get function. It's templatized, and you do Constexpr if.
Yeah, it's much shorter.
Say, well, if I've got a 0 here, return. So the interesting part of this function is it's returning two different types, right? In when you pass 0, it's returning a reference to an int. And if you pass in 1 as a template argument, it's passing a reference to a string. And we can still use auto as our return type, and the compiler knows that only one, normally you can't use auto as a return type. Well, first, step one, you normally can't have two different return types in a function, right? I'm returning an int, or I'm returning a string. Step 2, you can't use auto as a return type if you have multiple, confusing return values. They all have to match.
Yeah.
So in this case, they don't match, and yet it all works because for any given
auto,
n, there's only one answer.
Yeah, I think it's a nice example to see how auto can play very well with generic code and makes you just lift that into a different way. And C++ 17 again makes a code which was tedious before really short now. And for these structured bindings, we have a question from the chat. Can you combine structured bindings with something like std ignore, that you ignore like one member which is returned?
Well, you could just, you have to put inside the square brackets has to be a variable name, and it has to be a unique variable name, a new variable that is unused. But, that variable is not taking up anything. It's if you don't ever reference that variable, the compiler just throws it away for you. So other than the fact
it's
that
just a reference.
Which, you're going to have dummy 1 and dummy 2. It's kind of ugly naming, and maybe we've talked about having underscore. I've been playing around with the idea of having underscore be the only variable that you could reuse the name.
Okay.
As an anonymous variable. Yeah, and you could do this as backwards compatible, sort of, such that if you have one instance of underscore, well, that's a normal variable. If you have 2 underscores declared, well, now from then on you can't access it. But that's probably, if it was anonymous, you want it to be anonymous anyhow. You're not accessing it. So that might be a future addition. The one other thing I wanted to mention about that C++ 17 if Constexpr with the static assert I got there. The first time I wrote this, I wrote if Constexpr n equals 0, return this. If it equals 1, do this. Else static assert false. And that doesn't work because that static assert false is still, it happens all the time. Like the compiler will complain about that because it's not dependent on n anymore. So you put the static assert at the top, which makes complete sense. And then everything's fine. But the first time I wrote this, I, pretty much saying static assert false anywhere in code is not going to compile, right? Which kind of makes sense. But my natural reaction was to put it in this else if, and I just had to switch it around a little bit. It's not a big deal. So that's that.
Then we come to the next example, which is deduction guidelines. I've seen that there was a talk at C++ Now about this, but I have no idea what deduction guidelines are. What is that?
So the basic idea is, if you think about pair in the, like C++ 14, you either have to say pair int string, and you're going to repeat that pair int string again when you construct it, or the only way to not repeat the type is to use auto or to use make pair, to just be like, hey, figure out the types for me.
So
everyone's always like, it's a pain in the butt to type that all out. So we really like pair to act as a constructor knowing the type. So instead of typing make pair now, you just type pair, open brackets, 17, comma, hello, and it goes, oh, I understand pair is a template, and your end pair has a constructor that from that constructor, it will tell me all the types. So you require pair to have a constructor that takes all the types in it, so it can deduce the right types for the template. And it just makes things shorter, and it makes things more clear. Everything else was just syntax getting in the way, and now it's more of the way you were thinking anyhow. You were thinking, make me a pair that had 17 and hello string in it, and don't make me think about what those types are, because it's obvious what the types are.
And I see this splits up in explicit and implicit.
Yeah, and I should change this because I forget what the right terms are, but there's a subtle thing about using the word explicit. What I'm trying to say here is that you can make these deduction guides explicitly by defining your own, or the compiler will implicitly configure out construction guides for you. But there's a conflict there. Explicit also means the constructor of the constructor guide can use the explicit keyword. So you can have explicit constructor, explicit deduction guides, and explicit constructor, implicit guides, and depending on what the constructor really is. But for my use here, it just means, did you write it yourself or did the compiler figure it out? So I have this example, struct thingy that has a T in it, and there actually has no constructor or anything, but I want that if you just say thingy and you pass in a type, I want it to do the right thing, and I want to automatically, in this case, convert char stars to strings. So I write this thing that kind of looks like a function signature or something. It looks kind of like a constructor signature. It just says, here's the constructor for thingy, and it points to that, hey, in this case, thingy takes a standard string.
Okay.
And then it magically works.
Let's move forward to template auto, and see that's just a little feature where you can now use just auto as a template argument. It's a tiny little feature, but man, I've wanted this a lot because I believe that, yeah.
It's awkward for the user, but it also makes it hard sometimes for templates to even make a nice API of a template where it's very clumsy. There's one interesting thing about this that I'm wondering about. Once we get concepts, you would like, in my examples where you have T here, if you have you want, or even the example on the right hand side of the example, C++17, where it says auto v. If that was a concept like integer v,
that will make more sense. That's true.
Well, if it's integer v, then do you mean that v is a value like 17, or do you mean that v is a type?
True.
And normally, auto has meant it's a type, but now we're saying auto means
it's a value. Yeah, right.
It's a value, and we'll figure out all the stuff for you. Auto. I mean, it still means auto in the sense of the compiler will automatically deduce what it needs to deduce, but I think there's a subtle thing we're missing. I would like to be able to say, I want v to be a value, and I want it to be integral, and I guess I would need a requires clause or something here. So I almost kind of worry if we are going to run into a conflict between these two, but people are already talking about how to resolve that, and it's not a big issue at all, but it does. It's kind of interesting that such a small feature can.
I think it's an important first step to have the Turing completeness for auto.
Yeah. I'm sure we need yet another Turing complete language inside the language. Yeah.
Okay, and I see like one really big feature which you also had featured last year at Meeting C++ was fold expressions, which is already peeking into the chat, and here's so fold expressions is some really cool thing which you can make C++17 code again much terser and much easier to use than previously.
Yeah, I'm hoping that this is one of the nicest examples of there's about half as much code on the right hand side as there is on the left hand side, and it's just not obvious. Anyone who tries to write, I've got this function here called sum, pass in however many arguments you want, and it'll sum them up. It's easy to say that function, but then if you were to sit down and write that function, you have to think. Templates made you think in this different way. It's kind of like the recursive way almost, or whatever, right? Every version of sum calls another version of sum until you get to the base version of sum, which is sure, it's a way of thinking, and we should, that's useful at times. But now it's so simple. You can just say, hey, look, there's however many arguments as we need, ... and add them up, ... And now there's only one function, not three, and it just works. There is an interesting part of putting the 0 in there to make sure, because this sum will even work if the number of arguments are 0, and then the template wouldn't know what the template wouldn't know what the type was because there's no arguments. So the 0 is in there to say, well, if there's no arguments at all, return 0, and that means it's int, right? So there is some subtle things. Well, for example, now I'm making this assumption that you're not trying to sum a bunch of strings together because you're not concatenating, which I don't think string should have had a plus overload anyhow for concatenation because it's not really the right thing.
That's quite a backchat.
Yeah. But there was a big discussion about how could we determine what the base value was. But it's like, no, you should type in the base value.
But this is a feature which
it's got to be 1, right?
So fold expressions is a feature which I think will become really, really important to many users once it's available.
Yeah, it's surprising how, to some people you look at that and you think, oh, this is way advanced template programming. I don't do template programming. But I ran into this just like in the last couple of weeks. I needed this just for logging stuff where I'm like, you need to shove a bunch of stuff out on a log with the shift operator. And I'm like, oh, this could be so much easier if I had fold expressions. And I ended up with macros and overloading the comma operator and go-tos, and it was quite the feat of ugliness.
Oh yeah. And the next feature, nested namespaces, I think that explains
pretty
itself.
Self-explanatory. Yeah. That's all there is to it. Yeah, I should mention this whole thing here. We're going in kind of in order here of language features. And then, and so now we're getting into kind of the smaller language features.
Okay.
And then we get to, after that will be the library features. And then if we've got time, there's also some talk about the TSs at the bottom. So yeah, the nested namespaces is just
So just
what everyone's asked for.
quickly, let's go through them. They're just single line examples. So you can even again we get to make our C++ short code even shorter with this example of nested namespaces, which spares you a lot of boilerplate code if you have to open a lot of namespaces. With a static assert, this is now also available without the message.
Yep, it just will. I mean, it's up to the compiler exactly what it's going to output, but basically it's going to output a stringized version of the condition itself. Right. So, I mean, there was a lot of times where people were writing exactly that thing as the string. Like in my example, you're just kind of repeating yourself. It's like, why do I have to do this? Just do it for me.
Yeah, and inline variables
are, it's funny, they're a small feature as well, but they're really handy, and they're also really controversial because inline variables make global variables easier, and we all agree that global variables are bad. But at the same time, sometimes it makes things easier, and it also really helps. There's cases where you would have a header-only library if it wasn't for this static variable inside my struct or whatever, and I need that variable to be living in a CPP file somewhere, just so it have its single instance had to be in a CPP file. Now that thing can just be declared in the header, and so the weird part about this feature is why do we use the inline keyword? Because in what sense is this thing being inlined? As it turns out, inline hasn't meant inline for years and years because the compiler is going to inline any function it wants to, whether you told it to or not. And when you ask it to inline stuff, it may or may not inline it anyhow. So inline has never, at least for a long time, hasn't meant inline. What inline really means is if the compiler sees this function 10 times, there's only really one. So it's to avoid the ODR violation, the one definition rule. So inline really means, hey, this definition, you've seen it before. They also called weak symbol linking. So if you have eight copies of this, when you go to link it all together, just pick one. It doesn't matter which one; they're all the same. So that's how inline really works for functions. And so we're doing the same thing on a variable. At the end of the day, when the compiler goes to link this all together, it's going to have 10 copies of this foo variable because maybe this header was included 10 times. And it's going to pick one of them as the variable to link with. And that's fine. We've told it. It doesn't matter which one you pick. They're all the same.
Okay.
And,
so it makes static variables a bit easier in C++, I see.
Yeah, and that's why it was controversial because a lot of people said, why do we want to make something that we don't think is a very good idea, make it easier? And it's like, okay, we know that static variables are typically bad, but sometimes they are the right thing. And people were doing this other ways. You could use templates to get around this problem because templates also have like magic ODR rules.
Yeah.
So it's like, people are just going to do it anyhow. So,
but let's give it to them. Let's go to guaranteed copy elision. That seems to be also interesting.
Yeah, so that's something that we've had we haven't had guaranteed copy elision, but we've had copy elision forever, it seems, long time. But it was always, you could pretty much guarantee it because every modern compiler does it, but technically you weren't sure whether a copy was happening when you return something out of a function or not. But now that it's guaranteed, you actually get one step further. My example here is a lock guard, which lock guards, you want them to live within a scope, and you typically don't want them to be copied around. It doesn't make sense to copy a lock guard. So here I have this lock guard struct that is not copyable or movable, and yet right below that I have a function that returns a lock guard. And magically that works because For one, the return statement itself is constructing the object right in the return statement. Yep.
Is this the standard basically just picking up something which has been done by the compilers anyways?
Yeah, it's picking up what it's, de facto standard, picking up what the compiler was already doing. But because it's now standard, you get this. Before, the compiler would only do it if you had a copy constructor. You had to have a copy constructor, and then it would not call it. But it had to be there. So now, even if it's not there, the compiler's like, when you say return this lock guard, I actually know where it's going to end up. I know where it's going to be constructed, so I'm just going to construct it in place. So what really happens is the pointer, the address of the at the very bottom, my foo function there.
Yeah.
That guard
variable will be constructed in place, right?
Yeah, that the address of that variable is passed to the function to say, hey, when you construct your return value, that's where it goes.
Okay.
Or the whole thing gets inline.
Yeah, that's like I really like copy. I really like that, and it's a thing which I use for a lot of reasons in C++ for a long time. There's actually a question to our previous feature, to the inline variables. Will the compiler check for inlines for the variables if the values are effectively the same?
Well, if they all initialize to the same value?
Yeah.
I think so. I think that is probably one of those ill-formed, no diagnostic required, probably, which means you're not supposed to do that. It's invalid, but the compiler isn't going to guarantee that it checks it, because it's probably actually a hard, it's not a compile time check, it's a link time check. But I'm not I can't say 100% on that, but I think I hope that your compiler warns you, because it just seems wrong, right? If you do that.
Okay, good. So then we get into a new topic, which is attributes. That's now really interesting. In a lot of cases, there are new attributes now which are coming to the language.
Yeah, and we have this rule about attributes, so far at least, is that any attribute we've added to the language doesn't actually affect anything, in the sense that a compiler is free to ignore the attribute, and it shouldn't change the code. So attributes are kind of just there as hints to the compiler, and all they're going to do is cause warnings. They're not going to change something from compiling to not compiling, or change the behavior of the program. So my first example, the fall through, you used to have a lot of switch statements have fall throughs, and people say that's really bad. You should always comment when you put a fall through. And then you have compilers who are trying to warn about fall through, because they know it's often an error, but if the compiler warns about it, it warns too often. So how do I tell the compiler that I really meant to fall through in this case? So now there's an attribute for that.
Okay, and then
so I've got
I see
that
there's
fall through attribute. You'll notice that it has a semicolon at the end of it, because it is a attribute on a statement. So you kind of need that semicolon there.
So then there's a no discard attribute.
Yeah, this one's actually quite nice, and it's there's an ongoing debate on where we will use it within the standard library, but or you can put it on the return of a function to say. So my example being that this empty function of my container of ints here, empty can be a noun or a verb.
Yeah.
So when you say empty, did you mean, really it's adverb, whatever, adjective. Some people might think empty, if you didn't know the STL very well, was a function that would make the thing empty. Like, please empty this container for me. So if you ever see someone who calls empty without checking the return value, you're like, wait a second, that's wrong. Empty doesn't do anything. The only value you get is seeing what it returns. So if you were to discard the return value of empty, that's almost guaranteed to be an error. So now you can mark something as being no discard, and the compiler will warn if you discard that thing. So in my first example, that is put on a function. And in my second example is you can put it on a whole class.
Yeah, on structs and classes. That's interesting.
I've got an error class here as an example, such that if you have a function that returns an error and you want to guarantee that people look at the error to check that, was there really an error or was it like success, you can put no discard on that whole class. And whenever it's returned from a function, the compiler will complain if you don't look at the return value.
Mm-hmm. And then also I see there's maybe unused.
Yeah, and that's kind of the opposite of all the rest here. That sometimes you do return something and you really don't care about the return value. I'm actually wondering if I put that in the right spot. Oh yeah, okay, yeah.
Yeah, so, it seems to make sense.
Yeah, the variable gets returned, and it's a local variable, and if none of the code accesses it, the compiler is going to complain, hey, you have an unused variable.
Okay.
But in my example here is the only place this variable is used is inside the assert. So you run your code in debug, and there's no compiler error because the assert actually looks at the variable. And then when you compile and release, you get warnings that it's an unused variable because the assert gets thrown away.
Okay, I see.
And that's the funny thing that's why it's not called unused, because in one case it did get used. So we just decided, if it's called unused and it got used, would you want a compiler warning? So it's called maybe unused. It's like, whether I use this or not, don't complain about it.
Okay, that's interesting.
And it works on functions as well, by the looks of my last little bit there.
Yeah, I was wondering about the void. So, okay, so that's interesting. So it seems now we go into the more interesting library things.
Yeah.
With string view, which is actually kind of a cool feature to have on C++ in the standard.
Yeah, so a lot of work that was done on library, and if you go back to like how big is C++ 17, there's a lot of nice things in the language half, and in the library half, I think there's a huge amount of new stuff in the sense of it's fundamental data types that we were missing, and what we call vocabulary types. These classes that, it's not that they're that fancy or anything, it's just that you want to be able to pass these classes between APIs. If I write an API and you write an API that are very specific to whatever we're working on, there's a good chance that they still talk to each other with things like strings and stuff. And a lot of cases, people were writing their own classes to wrap stuff up, where that you're then like, my library can't work with your library because you use a different string class, or I use strings and you use char stars, or you would get all these conflicts. And so we just start defining all these things that we call vocabulary types that you're going to use between APIs, and everyone will use them together. So string view is the first example of that. And my little story that I'm laying out here is that you may have had a function called parse foo that parsed out a foo out of a string, and you wrote this function. It took a const reference to a string, and then someone else is like, well, you know what? In my code over here, I just have a buffer. I don't have a const reference. Can you take a char star? And you're like, okay, I'll add a char star, and that's fine. And then someone's like, well, my char star doesn't have a null on the end. It's within a big other buffer. Can I pass you a char star and a length? And then you're like, okay, now I've got three interfaces to the same function, and then this other part of our code, we're like, hey, we don't use strings, we use our own string class, or maybe we use QString or MyString. Now I've got 4 interfaces to my function.
So one question.
Yep.
So far, I always thought that string view only works on an SED string, but it seems that you just need to have like a constant char array or a char array in the length. Is that correct?
Yeah, string view is basically a pointer to a contiguous buffer and a length.
Okay.
Contiguous buffer of characters, right? It automatically works with standard string. We have a conversion. I forget which way the conversion goes because we kept switching whether string has the conversion to string view or string view constructor takes a string. It actually works out. We decided that string view is actually the more fundamental type. So string view doesn't know what a string is. String has conversions to string view. Okay. So which is how we would like other people like Qt, hopefully, and maybe they already have, QString should have a conversion to an automatic conversion to
Yes,
standard string.
there actually is a talk about std string view and q string view.
Right.
Accepted for meeting C++. Mark Mutz will talk about this, and I'm really looking forward to that talk because Qt also has now its own string view, and I hope they're also like kind of doing this in a way that plays nice with std string view.
Yeah, and they have they have wide string and Unicode issues that.
Yeah.
I mean, so, they do Unicode better than the standard does, so they have to stop and think about.
Qt has definitely its edges over the standard in a few ways, and QString is one of them. But then also, in your next example, you have std optional, which is like really interesting, and you're combining this here with string view, by the way. That's nice.
Yeah. The optional, so yeah, it's basically continuing my same example. So my example had 4 different parse foo functions. With string view, you can have one parse view function, and it'll all work out. And then the next question becomes of this class is, how do I return an error if I can't parse out foo? And there's 7 different ways of doing errors, and I've only shown a few of them. But one of the ways you might want to do is instead of returning a foo object, you return an optional foo. You say that there's either a foo here or there's not a foo at all. If you're into functional programming like Haskell, there's the maybe monad and things like that. A lot of languages have this concept of optional. Some languages have the question mark as part of you can say int question mark.
Okay, I'm going to scroll to the usage example. This contains a bit more C++ 17 code. So this is very similar to Boost.
Yes, it is totally built
on Boost,
from Boost Optional. Boost Optional has been around for years and years, and that's since C++ 11. We've been taking stuff out of Boost and putting it into standard, right? That's where shared pointer and unique, well, not unique pointer, but so much stuff came out of Boost. We're taking more stuff from Boost. There is slight changes compared to Boost. I don't think they're very major, but you can see that when you get an optional, it kind of works like a pointer. That if you check if
it has
optional,
a bit similar semantics.
Yeah, it's a nullable type kind of thing, and then when you want to use it, you use the star operator to get the value out of it. I think that's pretty much it's pretty self-explanatory.
And then to me, the big surprise for C++ 17 was that we get variant.
It was a big surprise because, well, one, optional took a long time to get in. I'm part of that. I had issues that I wanted resolved, argued for, finally got them. But we put a lot of effort into optional to get it right, and I think we got it right. And we put it through a TS, even though it was already in Boost and everything. We put it through a TS just to make sure that the changes we made were valid. But then once we had optional in, variant, every question we had about variant, we just said, well, how does optional work? Because the variant is like a bigger optional. Instead of having optional is either a type or empty, variant is a type or another type or another type. So a lot of the questions are answered. The one question that wasn't answered automatically just by looking at optional is what to do. There's cases where the variant might not hold any type at all, and that happens when you convert from my variant of ABC. If I've got an A and I try to assign a B, and you get a exception thrown halfway through, and the variant is made such that it's really hard to get into this situation because it should be an A for as long as possible, and if the B constructor or something fails, you should be able to go back to the previous state. But and we use move operators for that whenever possible. But if you have a throwing move operator, you can, which I don't think anyone should do, but it happens anyhow. You can get in a state where the variant is empty. So that was a big controversy, and variant was going to be just put in a TS, and then at some point we just said, you know what, we really want variant, any, and optional to all three be in at the same time because they all kind of work well together. and if you don't have variant, you're going to use standard any, and it's not the right thing to use. So they kind of came together as a triple, and so we just said, can we really get this in and put in an extra lot of hours to make sure it's ready to be in.
Yeah, that's really surprised a lot of people that it got in. I also see in your usage example there is std visit, so this is kind of a way to visit automatically this variant then.
So my example on the one side is a union. We're trying to replace a union because unions are very unsafe, but you always have a union, and the type that's inside the union is a separate variable. So now that's all bundled into the variant. It knows which type it currently is. So, but then you get in this hard situation of, well, how do I do, now that I have one of 3 types inside this variant, which one is it and how do I use it? You can do switch statements, and even in the new world in C++ 17, you could write it as a switch statement. But there's this thing called visit, which you pass in a class. In my case, I'm going to pass in a lambda, but you pass in a class that has overloads for the types that the variant could be, and it'll call the right overload based on what type the variant currently is. Now, I'm doing a trick where the lambda itself is templatized lambda, so even that looks really short, that lambda, that it uses an auto. So there's actually, because this variant has 3 types, this lambda is going to have 3 function call operator overloads for those 3 types. And they all call, I've got like 3 handle data functions. It'll call the right one with the right type magically based on which, it calls the right function, which is looks like a compile time thing, but it calls it at runtime based on what the current value of the variant is. So it's kind of magic.
Yeah.
And I kind of try to explain how that lambda up there works. That lambda gets...
And it's again converted. A very nice example how much shorter your own code gets with C++ 17.
Yeah. And I like...
This
is why all this stuff was done as tables. They're all before and after tables, because half the code goes away and you can see very clearly that your code is half as long as it used to be.
Yeah. Another thing which I like very much is I'm a current user of Boost variant, and Boost variant is one of the things which uses a lot of things or a lot of mechanisms in Boost which were once cutting edge and are today not anymore cutting edge. They're kind of rusted, and you kind of cut in form of long compile times yourself on it. And std variant gets to use all those new shiny features like variant templates, which a lot of things in Boost still don't use. So that's I'm looking forward to replacing Boost variant with std variant.
Yeah, that's a lot of the work that we did in the last little while on bringing in some of the new Boost stuff, some of the stuff from Boost was making sure it matches. It's kind of weird because when we bring something in, we're bringing it into, when we're bringing all these new Boost things into C++ 17, technically C++ 17 doesn't exist yet. So we can't expect Boost to already be written to C++ 17. But when we bring it in, we want standard variant to be using all the C++ 17 features. So that's some of the work we have to do whenever we bring a new library in, is to modernize it for
the libraries don't get copied from Boost. They get completely rewritten and re-implemented.
Yeah. And you just really have to check that.
So I scrolled to the last example for variant. So the last example is kind of obvious. So you can put different types into bar, and it only compiles if that type is in the variant, and if it's not, it's a compilation error. The first example under more usage, although this is practically, you can check if a certain type is in the variant, and you can then call std get on the variant. Correct?
Yeah.
And otherwise, get would throw.
Yes. Yeah, exactly. So you can just use standard get, sort of the same standard get that you use in tuples, but in this case, there's only one. The thing's only there if that type is currently active. So.
What happens if you have like the type twice in the variant? Is that possible, or?
Yes, you can have the same type multiple times. So maybe I didn't show that anywhere. I should probably update this. So you can call, in my example there, I'm calling get int and I'm calling get double.
Yeah.
You can also get 0, get 1, get 2. You can get the value
by index. Okay.
So
that makes sense. Yeah.
If you have 2 ints in there, you could ask for by the order you put them in the template argument list.
Okay.
If you do call get int and there's 2 ints in the variant, I think we make that a compile time error because it's ambiguous which one you want, which is probably better than just picking the first one or picking the current one. And where this sometimes happens is where I could easily have a struct that has an int for number of things, and then I've got a handle as my other thing in there, and on my OS this handle is a pointer, but I switch to another OS and that handle is an integer, and now I've got 2 ints in my variant, and suddenly it's not clear when I say get handle that's also an integer. So
that's true.
Yeah, so we're worried that people will run into that, and if we just made it compile, there was a chance we would do the wrong thing. So we will not compile if you call get int and there's 2 ints in your variant. In that case, you probably wanted to switch your code to using the indexes. And if it gets any more complicated than that, then you probably wanted types with actual names, and maybe you're beyond variant at that point. But, well, we hope to get a language variant that can name the values, just like a struct. The difference between a tuple and a struct is that tuples have names.
Yeah.
Structs members have names. Tuples don't have names.
Right.
That's the only thing we're missing in variant. If we do a language variant at some point, you will get names for your values inside.
Yeah. That could be interesting, a language variant, but that's a long time from now.
Yep.
Let's move on to std_any, which is also again a type which comes through Boost into the standard.
Yep.
So.
So this one is, and this one I think is more. We didn't touch this one very much. We just pulled it straight from Boost, either because it just happened to work, or maybe we missed something that we should look at. But it seems like it has less template magic than the other one, so we didn't have to update it as much for new stuff. But standard any is, you kind of can think of it as a variant, but you don't know what types it might be. So it can hold any type. Where optional is kind of like a better pointer, like a better nullable thing. Variant is a better union. Any is a better void star, right? In old code where you just want, I need to hold a value, and I don't.
We have a question from the chat.
Yes?
To one of the last variant examples, holds alternative. That is in the standard, correct?
That's in there. That's in the standard, yeah.
Okay.
That's standard : holds alternative. Yeah, I think I named it right. The great thing about me putting this up on GitHub is that I've had tons of corrections. So I don't get to work in open source very much, just because of the way my career went. But this is like this to me is an open source project.
So you're accepting pull requests?
Yeah, I love it. All I've done since I posted this is hit accept on a bunch of fixes.
Okay.
And I love it. It's great. I also accept fixes that aren't even just technical fixes. Fixes where like, hey, I think this would be more clear if you said this. It's like, great.
Yeah.
Yes.
So going back to variant, in your first example, we see that instead of a void pointer, you can instead of a void pointer, you can use any now, and any can take any value, any type, and is then initialized, and it also can be like it can have a null value. Then if you access it, it will throw, and so you can check if it has a value, and then you can use the any cast, on that object with a type, and if that type is not the correct type, it will throw. But you also could check if the type is correct with type ID, and then any cast, of course, will not throw because you checked for that previously.
Yep.
And
yeah, the only requirement on the thing you put in any, it has to be copyable, I think, is basically the only requirement. So any kind of normal type will work.
So basically, kind of like types. How about a movable type?
I think it needs to be copyable because standard. So any isn't a template, so that it has a copy constructor, right? And we can't say, well, in this case it doesn't have a copy constructor because it uses a movable type. It has a copy constructor, so it's going to turn around and copy. It uses type erasure and magic. It's going to turn around and copy that value, and therefore it assumes that whatever things you put in have copy constructors or copy operations.
And then there's also an interesting thing which is not finally in the standard file system. That's also great to have.
Yeah, and here's my great example of, and I should mention that a lot of these examples and a lot of this work wasn't done by me. Somewhere in here is credits, but JF Bastian and Bryce and a bunch of people.
Yeah, you can see the contributors of the repository on GitHub.
Yeah, so this big example here was written by somebody else, but I love this example because it shows how much code you used to have to write to get file system stuff. And in particular, the code had to be written completely different on Windows as it did on a POSIX machine, or if you had some other OS, it all had to be different. And now it's less code, and it's only written once. And I don't actually know a lot about the file system, but I mean, that was the whole intent, was to make this code be written only once.
Oh, I see we have John Korb in the chat. Welcome, John. So I actually did a talk on comparing Boost and Qt at C++ now, and in the spring I found out that Boost file system cannot copy directories. So this copy function which you see here, that is not in Boost. And I kind of, thought, well, Qt is so much better in that kind, so let's look up how Qt does it, and Qt then also has not this as supported. So Qt also cannot, out of the box in vanilla code, copy a directory. And then I looked it up in the standard, and with C++ 17 we are able not only to have file system but also to copy directories, which every now and then you need that. And you can go and look over Google on the solutions how to do it with Boost or Qt. But that's not needed anymore. The standard is there, superior now. And what I especially like is that actually what this example doesn't really show really good. It should more highlight this. You have a third parameter in copy, which is copy options. And so you can really put together the way a directory is copied, like do you want to copy subdirectories, do you want to copy symlinks, etc. And so this is really well thought through, and is really a good addition to the standard.
Yeah, that's interesting that I like that they have that option. You obviously know more about this than I do. Although my first thought about whether it should copy recursive or not is copy or copy not, there is no shallow. That is my Yoda saying, at least for classes. Maybe it doesn't apply to directories. But yeah,
okay.
There you go.
So do you have another example, or can we go on to the
well, I think you said
there's something, a next big feature, parallel SDL. This is really big and good feature. We had that in the first show of Meeting C++ Live. So can you give me some background on this more? Is there more examples?
I'm not an expert on it, but There was a parallel. This came from a TS, and basically we've taken all or almost all of the algorithms inside STL and parallelized them. So that alone just sounds awesome, and it is awesome. And so I've listed all the functions that are now been parallelized.
Yeah.
And I got to admit, there's a couple of them in there that parallelizing doesn't really help you any. Just one or two where if you actually go off and try to parallelize it, it's not going to turn out to be faster because of the overhead.
Mm-hmm.
But for the vast majority, you'll get great improvements with parallelization. And I think it's nice to be consistent that they all just have that parallelization. So the way it's done, it's the exact same function name, but for each of those functions, you can now pass a initial parameter. Usually you add optional parameters at the end, but in this case, it makes more sense to add the parameter at the front because then we can see the type right away that it's this special tag type.
Yeah.
And you can tell.
I think it's also important to distinguish between the old algorithms and the parallel algorithms.
Yeah. Yeah, and some of those algorithms might already have default parameters on them, on the end or whatever.
Yeah, right.
So and it's not just parallel. There's different levels of parallel, which I'm not quite an expert on. But so the first option is called sequential.
Yeah.
Which is basically not parallel. It's the parallel option that's going to call the old style, and then you can say par for parallel, which will spread it out on multiple threads.
Yeah.
And par unsequenced will actually can be on multiple threads and vectorized. So it all comes down to all these functions are working over a container, and they're going to call, star on the iterator. They're going to access the values in the container. So and then they're also going to call maybe operator less or whatever else they need to do. So the question is, what do your functions there do? Does your operator less do anything crazy like grab a mutex?
Yeah.
Hopefully not. That would be insane. Or does your star access of your iterator do anything? That's the only question of, can that be vectorized and can that be run on multiple threads? Probably, if you're just using pointers, you're just using standard containers and everything, it can all be use the power option of par unsequenced.
Yeah, it's an interesting option, but I think once we all have access or want access to C++ 17 is more optional to the general C++ programmers. I think we will see a lot of people like showing how much this actually brings in our usual C++ code. But like one thing which comes to my mind, it would make sense to have that also for ranged 4, which I think we currently don't. So
yeah,
there is a for each, and basically that's a ranged 4.
Yeah, we have a lot of code in our code base where we use, I think somebody's parallel for kind of magic thing where you pass a template or lambda into. Yeah, something like that I could see being nice.
Okay, so John Kolb asks, is the library allowed to use sequential when it is able to kind of determine as a default when parallelization would not bring anything?
Yeah, I think it is. I think all of these will come down to quality of implementation, right? Obviously, some of them aren't going to vectorize if you're on a tiny chip that doesn't vectorize. So, and you could theoretically call this stuff on machines that don't have multiple threads or whatever, right? We always try to not force things upon. For some reason, this C++ is really good at talking about either machines that no one's invented yet or machines that people invented 50 years ago, and we want to work on both of those still. So
yeah. So one other question from the chat is how many threads will this create? And I think that brings us a bit into the land of executors. and I think that is not defined in the standard how many threads it will create. That's, I think, implementation defined. Am I correct?
Yeah, it's all implementation defined, and a good implementation is going to create different number of threads depending on how big your container is, right? Because you kind of want bite-sized chunks, so it might be more what's the size of, like, do I want a thread per cache line, or do I want a thread per 10,000 items, and different algorithms will have different numbers. So there's a whole area of research for implementers to dive into to see how do you get the best out of this.
Yeah, and I think probably the maximum should be how many cores you have on the machine accessible.
Yeah, of course. That's the typical thing is there's not much sense having more threads than you have cores, basically, or depending on what you think about hyperthreads and stuff.
But to me, this feature is like so important because we really need more ways to do parallelism in C++, and we're still lacking so much in that field. And we have a lot of movement there, especially with the executor work, which is now done. But it's too late for that work to come in this standard. The executors has to make it in 20.
Area. It's a huge area, and in my mind, there's a lot of parallels, which makes it scary. There's a lot of parallels between executors and allocators, in the sense of they don't seem that similar, but they're both trying to manage this other resource, right? Allocators manage the memory resource, which for a lot of code you
interesting point, yeah.
And executors are trying to manage this shared resource of CPU or processing unit, and a lot of your code, you're like, I don't really want to think about that. But then it's C++. Sometimes you need to think about that because we want to, people want to work really low level sometimes. So it's like we need a mechanism to allow you, well, when you need to know, use an executor and you can control which, how this resource is shared. But like allocators, that's a complicated world, and we want to kind of get it right. So, which actually segues into the technical specs here. One or two of the technical specs down in this list is concurrency, parallelism, executors.
Yeah, let's go into the technical specifications. So this is the part now which is not in C++ 17, but it's in a lot of compilers available, either in the STD experimental namespace or as a feature as it is in Concepts, for example. Which is currently in GCC implemented.
Yeah, so I mean, if we think about it, C++ 17 is still technically not published, but we already have compilers that are, well along the way of having C++ 17 done. Mm-hmm. On top of that, we have compilers that already have all these TSs working. I mean, the one thing we don't have, I think, is a single compiler that has all of them. So you get this problem, well, I want to use concepts, use this compiler. I want to use modules, we'll use that compiler. If I want to use everything, every TS together, okay, you might have a hard time. So I think, somewhat surprisingly, Microsoft might be in the lead right now for being compiler closest to having all the TSs, which is great. They used to be the guys that were always last, and now it's a really close three-way race for who's the first compiler to have all of C++ 17, and who's the first compiler to have all of these TSs. And they're all very, very close. It's pretty exciting.
Are you familiar with Concepts?
I'm familiar with Concepts in that I know that they are I explain it either to people as, if you have a template, it has requirements, and it'd be great to have those requirements not as comments in your code, and instead those requirements should be built into the language, which is what my first example was trying to show in a nutshell. Yeah. That if you had a binary search with just took a T, which is some kind of iterator.
Concepts could make templates a lot more user-friendly.
Yeah, because otherwise it's like, what is this T? A lot of templates don't make sense unless you see an example of their use. It's like, oh, I'm supposed to pass an iterator here, or I'm supposed to do this. It's not obvious. One, this will make it more obvious what is being asked for, And if you don't do the right thing, the compiler will give you more obvious error messages. And then there's a whole tons of stuff on top of that. I'm just, just to call it something that gives you better error messages is way underselling concepts. It's going to help with overloading and instead of using enable if, and hopefully it is just it's the way like classes in object-oriented programming change the way people program. Concepts can change the way you program.
Oh yeah. And yeah, it would be nice that if we get concepts as a TS with the most C++17 implementation, so that it's kind of I know that, for example, in ranges v3, it's kind of simulated, and
Yep.
So if you want to use ranges, I don't know if you have ranges in here, that's also a different TS.
Yep.
That's already usable today as a third-party library by Eric Niebler for years, and that's really great. And then you have just here this list of, or just a short overview. Modules. Modules. I think we skip over modules. It's just it's a great feature, and it's working in Visual Studio, and they're working to make it working in Clang. So, Clang already has modules, but they're not like the standard ones, which we now go for, obviously.
The most amazing part of that, in my mind, is that there's people in Microsoft, the guys on Visual Studio team and people like that, are working on Clang. They're working on Clang for modules, or maybe not modules, but they're working on Clang for coroutines. So it's a whole new Microsoft.
Yeah.
Like it's amazing. So segueing to coroutines, I know that Gore was working to make coroutines work in Clang. So coroutines are like you see in a bunch of other languages. We have the await keyword and stuff. But it is kind of amazing. There's a couple of other proposals about coroutines. The one we currently have has some really neat hooks that you could do your own. We allow you to really hook into the whole coroutine system, which is kind of crazy but neat. And I suspect we'll get
it's really good for library writers. It's really detailed, and it's really nice. Coroutines is something which also is working on Microsoft compiler currently in Visual Studio, but it's also coming to Clang and to many other things. The networking TS is basically Boost Agio.
Yep.
And when talking about networking, there is currently a review of a library called Beast, which is for HTTP in C++ and coming to Boost. If you're interested, like to do HTTP on top of Agio, that would be a good place to go. And there's currently also a review if you want to participate in that. And then there's a lot of other TSs which are out there. And I see that the last part of this here is you're just giving people a lot of sources where to go for C++17. There is obviously also a repository from JF Bastian, which you already mentioned. A few other repositories on GitHub, and B. Philip Peck, a blog, a really good C++ blog, is having a C++17 wiki kind of thing with all features listed. And of course, cppreference.com is also a very, very good way to see what is new in the language or what is in the language.
Yeah, I should update this list too, because like even Bryce did a talk at CPP Now, which is, yes. I should put a link. It's now online. It's on YouTube, and a lot of that was based on this work, which was in turn based on his earlier work. So, and in particular, he has he has some better examples of my example of optional just uses it as error handling, which isn't the nicest. It's not the only way to use optional. He has some really nice examples in his talk of like, you look at it and you're like, yes, I can see how that's.
Yeah, I attended his talk and I really liked it. It was a good talk. And there's also James. There's a talk for C++17 in my conference probably, and there's a lot of. I guess that C++17 is going to be a big feature at CPPCon too. So if you're interested to be on this, like, more up to date, there's a lot of links. And the talk from Bryce was great, and that's definitely a good resource. And I think he's going to do that again at CPPCon when we have probably C++ 17 ratified.
Yeah, I hope so.
Should be pretty much on its way. And with that, we are now at 1 hour 20. Thank you very much for being my guest today.
Yeah,
Tony.
It's fun. Yep.
So, any additions, anything you would like to say?
No, it's good stuff. Thanks for having me. I will also hopefully be at CPCon, so
That's great.
Hope to see people there.
Oh yeah.
I hope to see you there.
Oh yeah, that's why I'm going there, to see all of you.
Yep. Excellent.
That's always the fun part, to see all the other people.
Yeah.
And with that, I think we're going to end the live stream. Thank you for watching. Thank you for asking questions. That was quite an active live stream today. And see you next time. I have no idea who my next guest is, but I hope to have a second version up in second live stream in July, and maybe some guests in August. And we're probably going to have a Meeting C++ live episode again from CPPCon.
Are you coming
as
to,
we had at C++ Now.
Are you coming next week? Are you coming to the Toronto? No?
Oh, I wish I could. No, I don't have time for Toronto.
All right.
Yeah. All right. So
next time.
Thank you for watching, and see you next time at Meeting C++ Live.